So cool. Hello, everyone. Thank you for coming, and your my teammates from Talkdesk. Thank you for being here. So the purpose of this talk is to expose you enough vocabulary for any ideas that we can make sense of our documentation for the databases of our choice. This is not a deep dive into database data structures. It's more like an overview of some of the core data structures that powers our databases. And I really believe that after this talk, the ideas will help you to choose databases wisely. That's the main goal of this talk. So I'm Pedro. I'm working at Talkdesk, and I'm running the Papers We Love meetup in Porto. You can follow me on Twitter if you want. I tend to tweet a lot. If you don't know what Papers We Love is, it's a repository of academic computer science papers and a big community that loves to reading them. As you can see, there's lots of chapters around the world. So if you're interested, be my guest. So I will ask lots of questions. The first one is, why should you care? If you're an application developer, why should you care how the database handles storage and retrieval internally? You're probably not going to implement your own storage system from scratch, at least on your day job, but still you'll need to select a storage engine that is appropriate for your use case. And for that, you'll need to have a rough idea of what the storage engine is doing under the hood. So this example is the simplest possible operations, and this is usually called a log, an append-only immutable log. So if you look at it, every time that we call dbset, we are appending a key and a value to a database file. So if you call with C1, A1, and B1, if you read what is it in the database file, it will be something like this: a key and a value. So this concept, this idea of a log, an immutable log, was introduced in '91. It has my age, so it's quite it's old. So the paper was called the design and implementation of a log structured file system, and the paper was presenting a new technique for disk storage management. And quoted from the paper, a log structured file system writes all modifications to disk sequentially in a log-like structure, thereby speeding up both file writing and crash recovery. So the main goal, the essence of a log, is to collect large amounts of new data in a file cache, always in main memory, and then write the data to disk in a single large I/O operation. So as you can see, the solution is to break the log, the immutable log, into several immutable segments of a certain size. And we close each segment when it reaches that specific size. And the subsequent writes will be targeted to new data file segments. So again, the goal is to collect large amounts of data into memory and then use a single I/O operation to flush the data to disk. So we are always appending stuff instead of updating or even deleting keys and values. So our first concern is, how do we avoid running out of space? And the solution is to use compactation. So the idea is to compact the segments into smaller ones by picking the latest values and ignoring the older ones. Note that if you want to delete a given key, we need to append a special deletion record. It's usually called tombstone. And since compactation makes segments much smaller, we'll eventually have to merge several segments together at the same time as we are performing compactation. And this kind of process obviously can be done in the background thread while we can still serve the reads and writes using the old segment files. And after the merging process is finished, we have a new compacted merge segment instead of having several ones. So it turns out that an immutable append-only design is good for several reasons. And the first one is that sequential writes are much more faster than random writes. And since they are immutable, concurrency and crash recovery are much simpler to handle, and merging old segments avoids fragmentation over time. So far we've seen now how it is easy to perform fast writes, but how can we find a given value of the value of a given key in a fast way? So obviously the solution is to add an index. It is an additional structure that is derived from data, and it keeps some additional metadata on the side that will help you to locate the data that we want to search for. Although maintaining such structures incurs overhead, especially on writes. And for writes, it's impossible to beat the performance of simply appending stuff to a file. So talking about examples, the simple possible indexing strategy is to keep an in-memory hash map where each key is mapped to a given byte offset. So it will look something like this. On the left, we have the in-memory hash map. On the right, we have the log structure file on disk. And this hash map will be used to find the offset in the data file. We'll have to seek to that location and read the value. So take for example, if you want to search for the object that contains the name Lisbon, we'll have to find the key. We need to search the key 101, get the byte offset, go to the file, take the byte offset. In this case, it's 20, and we'll have to move to the log structured file and start reading from the 20th byte, sorry, until the end of the line. So this is the way that we search for things. And it may look, or it may sound too simplistic, but it's actually a viable approach. In fact, it is essentially what Bitcask, the default storage of React, does. And Bitcask offers you high performance reads and writes with the only trade-off that all keys that you have must fit in memory. So this is quoted from the paper. When you read, keydir is actually talking about the in-memory hash table. So when a write occurs, the keydir is atomically updated with the location of the newest data. And the old data is still present on disk, but any new reads will use the latest version available in the keydir. This Okay, so this means that the in-memory hash map will always reflect the latest state of the database, since we can have old segments waiting for compactation that will never be accessible from the keydir. So the keydir always have the latest version available. So hash indexes are quite a viable approach, but they have some limitations. Obviously, they are not suitable for a very large number of keys, since the entire hash map must fit in memory. So you have to fit all of the keys that you have in your database in memory. And since they are not sorted, scanning over a range of keys is not efficient. It will be necessary to look up each key individually in the hash maps in order to return a range of keys. So to tackle this problem, in 2006, Google introduced Bigtable, a distributed storage system for structured data. And among other things, in the paper they introduced I think that it's called sorted string table, an SS table. It is basically it is a sequence of key value pairs that are sorted by key. So it's almost the same thing as an hash map, but is sorted by key. So by definition, and quoting the paper again, an SS table provides a persistent ordered, immutable map from keys to values where both keys and values are arbitrary byte strings. So an SS table is persistent, it is immutable, it's a map, and it's ordered. And because of this property, lookups can now be performed by first finding the appropriate block with a binary search in the in-memory index. And only then we'll read the appropriate block from disk. So this is kind of a representation of an SS table. We have on the left the in-memory index. As you can see, all of the keys aren't there. So, and on the right we have the sorted segment file on disk. So if you want to fetch, take for example the P key, we'll need to find it in the in-memory index, but it's not there. So we failed to find it, but we find M, which is close enough to P, and we start reading the file from M until we get the P. So that's how we search for things using an SS table. And the merging and compactation, it's the process. It's like the one used in the merge sort algorithm. We start by reading the segment file side by side. We look at the first key in each file. We copy the lowest key to the new segment file, and we repeat the process, and we'll have compacted and merged segments once again. So these kind of storage engines that are based on this principle of merging and compacting sorted files are often called LSM storage engines. And this concept of the log structure merge tree was introduced in 2006, and it describes an LSM-Tree as a disk-based data structure, and it is designed to provide low-cost index with a high rate of record inserts over an extended period of time. So you saw that the algorithm can be slow when we are looking for keys that do not exist in the database. So we first need to check the mem table. We then have to fetch all of the segments all the way back to the oldest before we can make sure that the key does not exist in the database. So the next solution for this problem was to introduce another data structure. It's called BloomFilter, and it is a memory-efficient data structure for approximating the contents of a set. Basically, it can tell you that if a key does not exist in the database, and this will save you many unnecessary disk reads for non-existent keys. So, but BloomFilters are a probabilistic function, so it can result in false positives. So the solution is to have a BloomFilter between the SS table, the in-memory index, and the sorted segment file on disk. And the in-memory index will ask the BloomFilter, do you have, for example, do you have a Z in your, is Z present in the BloomFilter? And the BloomFilter can reply with no. The key does not exist here, so the request for fetching Z stops right there. But it can reply with maybe, it maybe exists. And the in-memory index proceeds with the disk seek, and eventually it will find the Z key. But in this case, the BloomFilter will return a maybe, but it is a false positive because Z is not present in this, at least in this sorted segment file. So we will proceed with the disk seek. We fail to find the key, and we'll move to the next SS table and repeat the process until eventually find the Z key or not. So we have now a clear vision on SSTables, and we know that there are advantages over hash indexes. We know that when multiple segments contain the same key, the value from the most recent segment is kept, and older segments are always discarded. And in order to find a particular key in the file, there's no longer need to keep the full index in memory. We can use binary search for such thing. For now, we will be talking about append-only data structures, and which is the case of LSM-Trees and hash tables. Hash index, sorry. We'll now move to a new kind of structures. It's called update in place. And one example of update in place structures, it's called Btree. And they were introduced in the 70s with the paper on the left. And less than 10 years later, they were already called ubiquitous because they were being used everywhere. And they remain the standard index implementation in almost relational databases, and many non-relational databases use them as well. So a Btree is an index, obviously, and it is organized in pages of fixed size, capable of holding up to 2K keys, but pages need only to be partially filled. So basically, a Btree breaks the database down into fixed size pages and read or write one page at a time. So this is a roughly representation of a Btree. We have pages. Each page can be identified using an address, and each address allows one page to refer another page. And one of these pages is designated the root of the Btree, is the first page. And whenever you want to look up for a key in the index, we always start from the root of the Btree. So take for example, if you want to look up the ID 15, we'll start from the root. We go to the address that links to pages that contains values lower than 51. We'll go to the left. We go to the address that is pointing to a page that have keys greater than 11 and lower than 20 until we get to our key, the 15. So one property of Btrees is that they are balanced, and in order to keep a tree balanced, we must perform rotations. So on the left we have an unbalanced Btree after adding the node 2, and on the right we have our tree after a rotation, and as you can see, the maximum depth of the tree has decreased. As we know, the pages must be partially filled. This is another property of Btrees. So whenever we are adding a new key and there is no space to accommodate that key, we need to split a page in two and apply a rotation. So in this case, on the left, we are adding the key 11, and since the pages must be partially filled and there's no space to accommodate the key 11, we must split the page in two and apply a rotation. But you see that these update in place operations require that different pages to be overwritten. And in the latest examples of rebalancing and splitting the pages are kind of dangerous operations. Because if the database crashes after only some pages have been written, you end up with a corrupted index. And we don't want to end up like that. So the solution is to add another data structure. And it's called write-ahead log, also known as redo log. So They are used to restore a Btree back to a consistent state always after a crash. So, but this means that all modifications must be written before it can be applied to the pages of the tree itself. So we write these modifications into the write-ahead log. This means that we have to write every piece of data at least twice. And this kind of phenomenon is called write amplification. Is when you write, for a given write to a database, you result in multiple writes to disk. This is called write amplification. And obviously, it has a direct performance cost because you are writing at least twice. So the more that the storage engine writes to disk, the fewer writes per second it can handle. So let's do a quick recap on the differences between Btrees and LSM-Trees. We know that Btrees are mutable because they allow in-place updates. And instead of appending only, we can insert, we can update, and even perform deletions. And we know that writes are slower on Btrees because they must write every piece of data at least twice. That's called write amplification. And we need to write it once on the write-ahead log and once to the tree page. But also, they are read optimized. We can perform fast reads. On the other hand, LSM-Trees are immutable. They are written on disk once and they are never updated. So we can delete segments, but we can never update them. And this means that reads are slower on LSM-Trees because they have to check several data structures at different stages of compactions. As we saw, we have several data structures. We need to fetch several data structures to fetch a given key, although they are write optimized. And a last point is that LSM-Trees are able to sustain a higher write throughput due to the lower write amplification and because we have sequential writes. But we need to take in account maintenance. Maintenance is required due to compactation. So we need to do things, and this may affect the write throughput. So the last question is which one of the storage is the best type of storage? And I believe that the answer is there's no quick and easy rule for determining which type of storage engine is better for your use case. You shouldn't pick databases based on hype, and I see lots of people doing it. You should always test against your use case, and the final advice is that you should read papers as well. And we have papers we love. It can help you to find really great papers about data structures. So yeah, that's it for me. Thank you for coming.